Hello there, and welcome to Whispered Knowledge. I'm so glad you found your way here tonight. Maybe you've had a long day of looking up at the stars, wondering what's out there beyond our small blue planet. Or perhaps you're the kind of person who finds peace in contemplating the vast cosmic ocean that surrounds us. Either way, you're exactly where you need to be. Tonight, we're embarking on a journey through 100 fascinating facts about space, each one a small window into the infinite. You've got nothing to do but relax, let your breathing slow, and allow your mind to drift among the stars and galaxies and mysterious forces that shape everything we know. Before we begin our cosmic voyage, if these gentle explorations help you unwind or give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one curious soul at a time. Now, let's begin our journey through the universe. The birth and evolution of the universe. Fact 1. The universe began approximately 13.8 billion years ago in an event we call the Big Bang. This wasn't an explosion in space, but rather an expansion of space itself. In the first fraction of a second, the entire universe was smaller than an atom, filled with unimaginable energy and heat. Then, it began to expand, and it hasn't stopped expanding since. Every galaxy, every star, every atom in your body traces its origin back to that singular moment when everything we know burst into existence. The universe wasn't born in a place, it was born everywhere at once, a flowering of space-time that continues to unfold around us. Even now, as you listen to these words. Fact 2. The cosmic microwave background radiation is the oldest light we can observe in the universe. About 380,000 years after the Big Bang, the universe had cooled enough for the first atoms to form. Before this moment, the cosmos was opaque, filled with a hot plasma, where photons couldn't travel freely. But when electrons combined with protons to form hydrogen atoms, light was suddenly released. That ancient light has been traveling through space ever since, stretched by the expansion of the universe into microwave wavelengths. Today, it fills all of space with a faint glow at a temperature of 2.725 degrees above absolute zero. It was discovered by accident in 1964 when two radio astronomers, Arno Penzias and Robert Wilson, detected a persistent noise in their antenna that seemed to come from everywhere at once. They had found the echo of creation itself, the afterglow of the Big Bang, still reverberating through the cosmos. This discovery earned them the Nobel Prize and gave us one of the strongest pieces of evidence for the Big Bang theory. Fact 3. The universe is expanding, and that expansion is accelerating. Edwin Hubble discovered in 1929 that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This wasn't because galaxies are flying through space, but because space itself is stretching, carrying the galaxies along like raisins in rising bread dough. But in the late 1990s, astronomers discovered something even more mysterious. The expansion isn't just continuing, it's speeding up. Something is pushing the universe apart with ever-increasing force. We call this mysterious something dark energy, and it makes up about 68% of all the energy in the universe. We don't know what it is. We can't see it directly, but its effects are undeniable. The universe is not just expanding, it's being driven apart by an invisible force we barely understand. Fact 4. In the cosmic microwave background, we can see tiny temperature fluctuations that are like fingerprints of the early universe. These variations are incredibly small, about 1 part in 100,000, but they're monumentally important. They represent slight differences in density in the primordial soup of the early universe. Where the temperature was slightly higher, matter was slightly denser. Over billions of years, gravity pulled matter toward these denser regions, and they grew into the first stars, then galaxies, then the vast cosmic web of galaxy clusters we see today. Every structure in the universe, from the smallest star to the largest supercluster, grew from these quantum fluctuations in the fabric of the early cosmos. The universe we inhabit, with all its complexity and wonder, emerged from noise, from random quantum jitters amplified across cosmic time into everything we see. Fact 5. The universe was once opaque, then became transparent in an event called the Epoch of Recombination. For the first 380,000 years after the Big Bang, the universe was too hot for atoms to exist. Instead, it was filled with a dense plasma of protons, electrons, and photons, all bouncing off each other constantly. Light couldn't travel more than a tiny distance before colliding with a free electron. It was like trying to see through fog, so thick you couldn't see your hand in front of your face. But as the universe expanded and cooled, it reached a critical temperature around 3,000 degrees Kelvin, where electrons could finally bind to protons and form the first neutral hydrogen atoms. Suddenly, photons were free to travel unimpeded through space. The universe became transparent, and the light from that moment is what we now detect as the cosmic microwave background. Before recombination, the universe was a glowing fog. After it, space became dark and clear, dotted with the light of forming stars. Fact 6. Most of the universe's ordinary matter was created in the first 3 minutes after the Big Bang. During this brief window, temperatures were high enough for nuclear fusion to occur throughout the cosmos. Protons and neutrons came together to form the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium and beryllium. About 75% of the ordinary matter became hydrogen, about 25% became helium, and tiny fractions became the other light elements. Everything heavier than these, all the carbon in your cells, the oxygen you breathe, the iron in your blood, would have to wait for stars to form and forge these elements in their nuclear furnaces. The universe started simple, with just the lightest elements, and through billions of years of stellar alchemy, it became chemically complex enough for planets and life to emerge. Fact 7. Dark energy wasn't always the dominant force in the universe. In the early universe, gravity from matter dominated, slowing the expansion. But as space grew larger and matter became more spread out, its gravitational influence weakened. Meanwhile, dark energy, which appears to have a constant density throughout space, became proportionally more important. About 5 billion years ago, dark energy took over as the dominant force, and the expansion began to accelerate. This means the universe went through a transition from a time when gravity was trying to pull everything together to our current era, where dark energy is pushing everything apart. We're living in the early stages of an accelerating expansion that may continue forever, with galaxies beyond our local group eventually racing away from us faster than the speed of light, disappearing beyond an ever-shrinking cosmic horizon. Fact 8. The observable universe has a radius of about 46.5 billion light years, even though it's only 13.8 billion years old. This seems impossible at first. How can light from something 46.5 billion light years away reach us in a universe that's only 13.8 billion years old? The answer lies in the expansion of space. When light left the most distant galaxies we can see, they were much closer to us. But during the billions of years the light was traveling toward us, space itself was expanding, carrying those galaxies away. By the time the light reaches us, those galaxies are now 46.5 billion light years distant. The observable universe is like a sphere around us, constantly growing, but the edge isn't moving because of motion through space. It's moving because space itself is expanding underneath everything, stretching the very fabric of reality. Fact 9. Inflation theory suggests the universe underwent a period of exponential expansion in the first fraction of a second. According to this theoretical framework, sometime around 10 to the power of minus 36 seconds after the Big Bang, the universe may have expanded by a factor of at least 10 to the power of 26 in an incredibly brief moment. In less than the blink of an eye, space could have grown from smaller than an atom to roughly the size of a grapefruit or larger. This would help explain several puzzles about why the universe looks the way it does, why it's so uniform, why it's so flat, and where the tiny density fluctuations that seeded galaxies came from. During inflation, quantum fluctuations might have been stretched to cosmic scales, becoming the variations in density we see in the cosmic microwave background. The entire observable universe, with all its billions of galaxies, might have originated from a patch of space smaller than a single proton, inflated to cosmic proportions, in less time than it takes light to cross the nucleus of an atom. Fact 10. The universe might be much larger than the observable universe, possibly even infinite. Everything we can see is limited by the distance light has had time to travel since the Big Bang. Beyond that horizon, there's likely more universe, but we can't observe it because the light hasn't had time to reach us yet. Based on different theoretical models, the universe could extend far beyond what we can see, or it could even be infinite in extent. Some theories suggest the universe might be like a three-dimensional surface of a four-dimensional sphere, curved back on itself, while others propose it's flat and extends forever. We may never know the true size or shape of the entire universe. What we observe might be just a tiny bubble in an endless cosmic ocean, one small region among countless others, each beyond our ability to ever detect or visit. Stars, birth, life, and death. Fact 11. Stars are born in vast clouds of gas and dust, called stellar nurseries or molecular clouds. These clouds can span hundreds of light years across and contain enough material to make thousands or even millions of stars. They're cold, just a few degrees above absolute zero, and incredibly dark, thick with dust that blocks visible light. But within these dark cradles, gravity is always working. Small regions become slightly denser, and as they do, they pull in more material. The cloud begins to collapse, spinning faster as it shrinks, heating up as gravitational potential energy converts to thermal energy. Over hundreds of thousands of years, a dense core forms, growing hotter and denser until finally, at temperatures of about 10 million degrees Kelvin, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing tremendous energy, and a star is born. The pressure from this fusion balances the inward pull of gravity, and the star settles into a stable existence that can last millions or billions of years. Fact 12. Our sun converts about 600 million tons of hydrogen into helium every single second. Deep in its core, where temperatures reach 15 million degrees Kelvin and pressures are 250 billion times Earth's atmospheric pressure, hydrogen nuclei are moving so fast they can overcome their mutual electromagnetic repulsion and fuse together. In each fusion reaction, a tiny amount of mass is converted directly into energy according to Einstein's famous equation, E equals mc squared. The sun loses about 4 million tons of mass every second, completely converted into the energy that warms our planet and makes life possible. It's been doing this for 4.6 billion years, and it has enough hydrogen fuel to continue for another 5 billion years. The sunlight touching your face right now started as fusion reactions in the sun's core, then spent tens of thousands of years bouncing around inside the sun before finally escaping as light and crossing 93 million miles of space in just over 8 minutes to reach you. Fact 13. The most massive stars can be more than 100 times the mass of our sun and shine millions of times brighter. These stellar giants are incredibly rare and incredibly short-lived. While the sun will burn for about 10 billion years total, the most massive stars exhaust their fuel in just a few million years. They burn through their hydrogen so quickly, fusing it into helium, then helium into carbon and oxygen, then continuing through progressively heavier elements all the way to iron. They're like cosmic candles burning at both ends. Brilliant, but brief. The massive star R136A1 in the Large Magellanic Cloud is estimated to be somewhere between 170 to 265 times the mass of the Sun, with recent observations suggesting it might be toward the lower end of that range. It shines with the power of millions of suns. If it were placed just 30 light years from Earth, it would appear as bright as the sun in our sky. Some of these massive stars end their lives in the most energetic explosions in the universe, supernovae that can outshine entire galaxies for a brief moment. It's so luminous that if it were placed just 30 light years from Earth, it would appear as bright as the sun in our sky. Fact 14. When a massive star runs out of fuel, its core collapses in less than a second, triggering a supernova explosion. After millions of years of stable fusion, the star builds up an iron core. Iron is special because it can't release energy through fusion. It's the end of the line. Once the core is iron, fusion stops, and nothing can support the star against its own gravity. The core collapses catastrophically, shrinking from about the size of Earth to about 20 kilometers across in less than a second. The implosion is so violent that it rebounds, sending a shockwave outward through the star's outer layers. The star explodes with the energy of billions of nuclear bombs, briefly outshining the entire galaxy. All the elements heavier than iron, gold and platinum and uranium, are forged in these final moments, in the intense heat and pressure of the explosion. The debris scatters into space, enriching the interstellar medium with heavy elements that will eventually become part of new stars, new planets, and potentially new life. We are, quite literally, made of stardust, atoms forged in the hearts of dying stars. Fact 15. Neutron stars are among the densest objects in the universe. When a massive star explodes as a supernova, its core collapses into an object so dense that a sugar cube-sized piece would weigh about 1 billion tons on Earth, roughly as much as a mountain. These objects are typically only about 20 kilometers in diameter, about the size of a city, but contain more mass than our entire sun. They're made almost entirely of neutrons packed so tightly that the entire star is essentially one giant atomic nucleus. The gravity at the surface is so intense that if you could somehow stand on a neutron star, you'd weigh billions of times more than you do on Earth, and you'd be compressed to a thickness of less than a millimeter. These stellar remnants represent matter in a state that can't be recreated anywhere else in the universe. Laboratories of extreme physics spinning in the darkness of space. Fact 16. Some neutron stars spin hundreds of times per second. When the core of a massive star collapses, conservation of angular momentum means the rotation speed increases dramatically, like a figure skater pulling in their arms during a spin. Some neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like lighthouse beams. If Earth happens to lie in the path of the beam, we detect regular pulses of radiation, hence the name pulsar. The fastest known pulsar, PSRJ 1748-244680, rotates 716 times every second. Imagine an object more massive than the Sun, compressed to the size of a city, spinning so fast that a point on its equator is moving at about 1/4 the speed of light. These cosmic lighthouses are so regular in their pulses that they rival atomic clocks in precision, ticking away in the depths of space with mechanical reliability that spans millions of years. Fact 17. Magnetars have the strongest magnetic fields in the known universe. These exotic neutron stars possess magnetic fields about 1,000 times stronger than ordinary neutron stars, which themselves have fields trillions of times stronger than Earth's. A magnetar's magnetic field can reach intensities of 100 billion Tesla or more. At these strengths, the magnetic field becomes powerful enough to distort the very atoms that make up the star's crust. The field is so intense it affects empty space itself, creating virtual particle-antiparticle pairs. If a magnetar existed at half the distance from Earth to the Moon, its magnetic field would erase every credit card on our planet and pull the iron from your blood. These fields can cause the star's crust to crack in starquakes that release more energy in 1/10 of a second than our Sun produces in 100,000 years. When magnetar SGR 1806-20 flared in 2004, it released more energy in a fraction of a second than the Sun has released in its entire 4.6 billion year lifetime. Fact 18. White dwarfs are the remnants of stars like our Sun. When a star like the Sun exhausts its hydrogen fuel, it swells into a red giant, then gently sheds its outer layers into space, creating a beautiful planetary nebula. What's left behind is the hot, dense core, a white dwarf. These objects are about the size of Earth but contain roughly the mass of the Sun. A teaspoon of white dwarf material cell would weigh about 15 tons. They're supported not by fusion or thermal pressure, but by quantum mechanical effects called electron degeneracy pressure. Electrons, being fermions, cannot occupy the same quantum state, and this quantum resistance to compression is what prevents white dwarfs from collapsing further. They don't generate energy through fusion anymore. They simply cool slowly over trillions of years, gradually fading from white to yellow to red. The universe isn't old enough yet for any white dwarf to have cooled to become a black dwarf. But given enough time, this is the fate that awaits them, eventually becoming cold, dark spheres, drifting through the endless night of space. Fact 19. Some white dwarfs can explode as type Ia supernovae. If a white dwarf is in a binary system with a companion star, it can gravitationally pull matter away from its partner. As this stolen material accumulates on the white dwarf, its mass increases. There's a critical mass limit for white dwarfs, about 1.4 times the mass of the Sun, called the Chandrasekhar limit. If a white dwarf approaches this mass, electron degeneracy pressure can no longer support it. The star begins to collapse, and the compression heats the material to temperatures where carbon fusion can occur. The entire star undergoes nuclear fusion almost simultaneously in a runaway reaction. Within seconds, the white dwarf is completely destroyed in a thermonuclear explosion that can briefly outshine all the billions of stars in its host galaxy combined. These type A supernovae are important cosmic tools because they all have roughly the same intrinsic brightness, making them excellent distance markers for astronomers mapping the expansion of the universe. It was through studying these explosions that astronomers discovered the universe's expansion is accelerating. Fact 20. The Sun is a yellow dwarf star in the prime of its life. Our home star is about 4.6 billion years old, roughly halfway through its main sequence lifetime. It's quite ordinary as stars go, neither particularly large nor small, hot nor cool. But to us, it's everything. The Sun contains 99.86% of all the mass in our solar system. It's so large that more than 1 million Earths could fit inside it. Every second, it produces more energy than all of human civilization has used throughout our entire history. In about 5 billion years, when the hydrogen in its core runs out, the Sun will begin to change. It will swell into a red giant, possibly large enough to engulf Mercury and Venus, and maybe even Earth. During this phase, it will shed its outer layers, creating a planetary nebula, while its core contracts into a white dwarf about the size of Earth. But that's far in the future. For now, the Sun continues its steady burn, a middle-aged star in a quiet neighborhood of the galaxy, providing the warmth and light that makes life on Earth possible. Fact 21. Some stars pulsate, varying in brightness over regular periods. These variable stars expand and contract like beating hearts, their surfaces moving in and out as they brighten and dim. Cepheid variables, for instance, can vary in brightness by a factor of 2 or more over periods ranging from a few days to several months. There's a direct relationship between how long a Cepheid takes to complete one cycle and its intrinsic brightness. This means by measuring the period of pulsation, astronomers can determine how bright the star really is, and by comparing that to how bright it appears, they can calculate its distance. Henrietta Leavitt discovered this period luminosity relationship in 1912, and it revolutionized astronomy, giving us a cosmic yardstick to measure distances to faraway galaxies. These pulsating stars are unstable, caught in a delicate balance between the inward pull of gravity and the outward push of radiation pressure, oscillating between these forces in regular rhythms that echo across cosmic distances. Fact 22. Binary star systems are remarkably common in the universe. More than half of all stars exist in binary or multiple star systems, gravitationally bound to one or more companion stars. These stellar pairs orbit their common center of mass, dancing around each other over periods that can range from hours to millions of years. Some binaries are so close that they orbit each other in days or even hours, with stellar surfaces nearly touching. Others are widely separated, their stars appearing as independent points of light in the sky, bound only by the weak but persistent tug of gravity over vast distances. In some binary systems, matter can flow from one star to the other, creating spectacular phenomena like novae, or even triggering supernova explosions. Our Sun appears to be a solitary star, but it's in the minority. Most stars in our galaxy have at least one companion, partners in an orbital dance that can last for billions of years. Black holes and extreme gravity. Fact 23. Black holes are regions of space-time where gravity is so strong that nothing can escape, not even light. When a very massive star collapses at the end of its life, if the remaining core is massive enough, no force in the universe can stop the collapse. It continues to shrink, becoming denser and denser, until it forms a singularity, a point of infinite density. Around this singularity, there's a boundary called the event horizon. Anything that crosses this boundary, whether matter or light, can never escape. It's not that objects move fast enough to escape from inside the event horizon. Rather, space-time itself is so warped that all paths lead inward. The event horizon isn't a physical surface. It's more like a point of no return, a one-way membrane in space-time. From the outside, a black hole appears as a perfectly black sphere, darker than the darkest night, surrounded by the faint glow of superheated matter spiraling inward. They're cosmic predators, invisible except for their effects on nearby matter and light. Fact 24. The supermassive black hole at the center of our Milky Way galaxy is called Sagittarius A asterisk. It contains more than 4 million times the mass of the Sun, yet it occupies a space smaller than the orbit of Mercury. We can't see the black hole directly because no light escapes from it, but we've watched stars orbit around this invisible massive object for decades. Some of these stars whip around Sagittarius A asterisk in elliptical orbits, reaching speeds of up to 5,000 kilometers per second, more than 1.5% the speed of light, as they sweep close to the black hole. One star, designated S2, completes an orbit every 16 years, following Keplerian mechanics with such precision that we can measure relativistic effects in its motion. From these stellar orbits, we can calculate the mass of the invisible object they're dancing around. The Event Horizon Telescope captured the first direct image of the environment around Sagittarius A asterisk in 2022, showing the glowing ring of hot gas swirling around the darkness at the galaxy's heart. Fact 25. Nearly every large galaxy has a supermassive black hole at its center. These cosmic giants can contain millions or even billions of times the mass of the Sun. The largest known black hole, TOM 618, has a mass estimated at 66 billion solar masses. Its event horizon would stretch out nearly 1,300 times the distance from Earth to the Sun. How these supermassive black holes formed is still a mystery. Did they grow from smaller black holes that merged and accreted matter over billions of years? Or did they form directly from the collapse of massive gas clouds in the early universe? The James Webb Space Telescope has been finding supermassive black holes and galaxies less than 1 billion years after the Big Bang, so massive that they're difficult to explain with current theories. These black holes seem to have grown too quickly, suggesting we might be missing something fundamental about how they form and evolve in the early universe. Fact 26. When you fall toward a black hole, time dilates in a phenomenon called gravitational time dilation. According to Einstein's general theory of relativity, gravity isn't just a force, it's a curvature of space-time. The stronger the gravity, the more time slows down relative to an outside observer. Near a black hole, this effect becomes extreme. If you watched a clock fall toward a black hole's event horizon, you'd see it tick slower and slower as it approached. To you, the clock would appear to freeze at the horizon, taking an infinite amount of time to cross it, gradually fading from view as its light is redshifted to longer and longer wavelengths. But from the perspective of someone falling with the clock, nothing strange would happen. They'd cross the event horizon in a finite time, unaware of any boundary. Time is relative, and near a black hole, these relativistic effects become impossible to ignore, creating a strange disconnect between what different observers experience. Fact 27. If you fell feet first into a black hole, tidal forces would stretch you in a process called spaghettification. The gravity from a black hole becomes stronger the closer you get. This means the gravitational pull on your feet, if they're closer to the black hole, would be significantly stronger than the pull on your head. This difference in gravitational force across your body would stretch you vertically while compressing you horizontally, elongating you like a piece of spaghetti. For stellar mass, black holes, this stretching would begin outside the event horizon and tear you apart long before you reached it. But for supermassive black holes, the event horizon is so far from the singularity that tidal forces there are relatively weak. You could cross the horizon intact, though you'd still be doomed to fall toward the singularity, where tidal forces eventually become infinite. It's a strange fate, to be stretched into a stream of atoms, pulled inexorably toward a point of infinite density, while time outside continues at its normal pace, oblivious to your demise. Fact 28. Black holes can spin, and their rotation drags space-time around with them. When a massive rotating star collapses into a black hole, conservation of angular momentum means the black hole inherits the star's rotation, often spinning incredibly fast. A rotating black hole twists space-time around it in a process called frame dragging. Near the event horizon, this effect is so strong that nothing can remain stationary. Everything is dragged around in the direction of the black hole's rotation. There's a region called the ergosphere, outside the event horizon, where it's impossible to stand still relative to distant stars. You're forced to move with the rotation of the black hole, carried along by the swirling space-time. Theoretically, it might be possible to extract energy from a rotating black hole by dropping matter into the ergosphere and capturing the energy it gains from the black hole's rotation. These spinning black holes are nature's most efficient batteries, storing rotational energy in the fabric of space-time itself. Fact 29. When two black holes merge, they create gravitational waves that ripple through space-time. According to general relativity, accelerating masses create distortions in space-time that propagate outward at the speed of light. When two black holes orbit each other, they emit gravitational waves, losing energy and gradually spiraling closer together. In the final moments before merger, they're orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light, releasing more power in gravitational waves than all the stars in the observable universe combined. When they finally collide, they merge into a single black hole, ringing like a struck bell as it settles down. The LIGO and Virgo detectors have observed dozens of these mergers, detecting the gravitational waves as they pass through Earth, stretching and squeezing space by less than the width of a proton. It's a triumph of engineering and physics to detect such tiny ripples, echoes of cataclysmic events occurring millions or billions of light years away. Fact 30. The first direct image of a black hole was captured in 2019 by the Event Horizon Telescope. This wasn't a traditional photograph. The Event Horizon Telescope is a network of radio telescopes scattered around the globe, from Hawaii to Chile to Antarctica, all working together as a single Earth-sized virtual telescope. They observed M87*, the supermassive black hole at the center of the galaxy Messier 87, which is 55 million light-years away and contains 6.5 billion times the mass of the Sun. The image shows a bright ring of light surrounding a dark central region. This ring is light from hot gas orbiting the black hole, bent by the extreme gravity into a visible halo. The dark center is the shadow of the event horizon, the point of no return, silhouetted against the glowing disk. It's not the black hole itself, which is by definition invisible, but rather the absence of light, a hole punched in the bright background. This image confirmed predictions from general relativity and gave us our first direct look at the edge of a black hole. Fact 31. Hawking radiation suggests that black holes aren't completely black. Stephen Hawking proposed in 1974 that black holes can emit radiation due to quantum effects near the event horizon. According to quantum mechanics, empty space isn't truly empty. Virtual particle-antiparticle pairs constantly pop into existence and annihilate each other. Near a black hole's event horizon, it's possible for one particle to fall into the black hole while the other escapes. To a distant observer, it appears as though the black hole is emitting radiation. This Hawking radiation is incredibly faint for stellar and supermassive black holes, far too weak to detect with any current technology. But the smaller the black hole, the stronger the radiation. Over immense timescales, quadrillions upon quadrillions of years, black holes would slowly evaporate away through this process, losing mass until they eventually vanish in a final burst of energy. This means black holes aren't eternal. Given enough time, they too will fade away, leaving nothing behind but a whisper of radiation spreading through empty space. Fact 32. We detected the first possible runaway supermassive black hole in 2023. Normally, supermassive black holes sit at the centers of galaxies, held there by gravity. But when two galaxies merge, their central black holes can form a binary system. If a third black hole enters the picture, the gravitational interactions can be chaotic enough to fling one black hole out of the galaxy entirely. The James Webb Space Telescope confirmed evidence of what appears to be a supermassive black hole rocketing through its host galaxy at about 2.2 million miles per hour. As it plows through the gas in the galaxy, it leaves a trail of newly formed stars in its wake, like a ship leaving a wake in the ocean. This runaway black hole challenges our understanding of galactic dynamics and shows that even objects with the mass of millions of suns aren't immune to being ejected from their homes, cast out into intergalactic space to wander alone. Our galaxy and beyond. Fact 33. The Milky Way galaxy contains between 100 and 400 billion stars. Our home galaxy is a barred spiral galaxy with 4 major spiral arms winding out from a central bar of stars. From our position inside the galaxy, about 26,000 light years from the center, we see it as a faint band of light stretching across the night sky. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, and the name stuck. We're embedded in the disk of the galaxy, seeing the concentration of stars when we look along the plane, and fewer stars when we look up or down out of the disk. Every star you can see with your naked eye is part of the Milky Way. On a clear, dark night, away from city lights, you might see a few thousand stars, but that's just a tiny fraction of the hundreds of billions that make up our galactic home. Most stars are hidden from our view by distance or dust, their light absorbed or scattered before it can reach us. Fact 34. The Milky Way is on a collision course with the Andromeda Galaxy. Andromeda, also called M31, is the nearest large galaxy to our own, about 2.5 million light years away. It's slightly larger than the Milky Way and approaching us at about 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will collide. It won't be a violent collision in the traditional sense. Galaxies are mostly empty space, and stars are so far apart that actual stellar collisions will be rare. But the gravitational interaction will dramatically reshape both galaxies. Their spiral structures will be destroyed, stars will be flung into new orbits, and over billions of years, the two galaxies will merge into a single large elliptical galaxy that astronomers have already nicknamed Milky Way. By that time, our Sun will be nearing the end of its life as a main sequence star, but if Earth still exists, future inhabitants might see Andromeda dominating the night sky, growing larger as it approaches, before the sky transforms into something unrecognizable during the merger. Fact 35. Dark matter makes up about 85% of all matter in the universe, but we can't see it directly. We know dark matter exists because of its gravitational effects. Galaxies rotate so fast that their visible matter alone couldn't hold them together. They should fly apart. Galaxy clusters contain more mass than we can account for by adding up all the stars and gas we can see. Gravitational lensing, the bending of light around massive objects, shows there's more mass present than meets the eye. Dark matter doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. It only interacts through gravity. We've built massive underground detectors trying to catch dark matter particles as they pass through Earth. But so far, we've had no confirmed detections. The nature of dark matter remains one of the greatest mysteries in physics. It outweighs ordinary matter by more than 5 to 1, yet we don't know what it's made of, what particles compose it, or how it formed. The scaffolding of the universe is invisible. Fact 36. The Milky Way has already cannibalized dozens of smaller galaxies. Our galaxy didn't grow in isolation. Over billions of years, it has gravitationally captured and consumed numerous dwarf galaxies. As these smaller galaxies orbit the Milky Way, tidal forces stretch them out, pulling stars away until they're torn apart completely. These stellar streams wrap around our galaxy like ghostly ribbons, the remnants of galaxies that no longer exist as distinct objects. One large merger, called the Gaia-Enceladus collision, happened about 10 billion years ago and added many stars to the Milky Way's halo. Right now, the Sagittarius dwarf galaxy is being pulled apart, its stars gradually joining our galactic population. The Milky Way we see today is like a composite photograph, made of many smaller pieces that have merged over cosmic time. Galaxy formation is a story of cosmic cannibalism, of smaller structures combining into larger ones, driven by the relentless pull of gravity over billions of years. Fact 37. There are hundreds of billions of galaxies in the observable universe. Every fuzzy patch of light visible in deep field images from the Hubble or James Webb space telescopes is an entire galaxy containing billions or trillions of stars. The Hubble Ultra Deep Field, one of the most detailed images ever taken of distant space, contains about 10,000 galaxies in a tiny patch of sky no bigger than a pinpoint held at arm's length. If that's representative of the entire sky, and astronomers believe it is, then there must be at least 100 billion galaxies in the observable universe, and possibly many more. Each galaxy is an island universe, a collection of stars, planets, gas, and dust, held together by gravity. Most are so far away that their light has been traveling toward us for billions of years. We're seeing them not as they are now, but as they were in the distant past. Some when the universe was young and galaxies were just beginning to form. Fact 38. Galaxies come in several basic shapes: spiral, elliptical, and irregular. Spiral galaxies like the Milky Way have flat rotating disks with spiral arms winding out from a central bulge. They're rich in gas and dust and actively forming new stars in their spiral arms. Elliptical galaxies range from nearly spherical to highly elongated shapes. They contain mostly older stars and little gas or dust, having used up or lost most of their star-forming material. They're often the result of galaxy mergers. Irregular galaxies have no particular shape, chaotic and disorganized, often disrupted by gravitational interactions with other galaxies. The Hubble sequence classifies galaxies along this spectrum, from ellipticals through spirals to irregulars, though we now know galaxy evolution is more complex than this simple linear sequence suggests. Galaxies can change types over time, transforming through mergers, gas loss, or gravitational interactions. They're not static objects, but evolving systems, changing over billions of years. Fact 39. The cosmic web is the largest structure in the universe. On the largest scales, galaxies aren't distributed randomly. They're organized into a vast network of filaments and sheets, with enormous voids in between. This cosmic web emerged from tiny density fluctuations in the early universe. Denser regions attracted more matter through gravity, growing larger over time, while less dense regions became even more empty as matter flowed out of them toward the denser regions. The result is a foam-like structure, with galaxies concentrated along filaments and at nodes where filaments intersect, and vast empty voids containing very few galaxies. The largest structures in this web are superclusters, collections of galaxy clusters spanning hundreds of millions of light years. Our Milky Way is part of the local group, which is part of the Virgo supercluster, which is itself part of the even larger Laniakea supercluster. This hierarchy of structures, from individual galaxies to the cosmic web, represents the universe organizing itself under the influence of gravity over 13.8 billion years. Fact 40. Some galaxies emit more energy than 1 trillion suns, powered by supermassive black holes. These extremely luminous galaxies are called quasars, and they're among the brightest objects in the universe. At their hearts are supermassive black holes actively feeding on surrounding matter. As gas spirals into the black hole, it forms an accretion disk, heating up to millions of degrees through friction and emitting tremendous amounts of energy across the electromagnetic spectrum. The black hole can also launch jets of matter and energy perpendicular to the accretion disk, streaming out at nearly the speed of light for hundreds of thousands of light years. Quasars are so bright that a single one can outshine its entire host galaxy of hundreds of billions of stars. Most quasars we observe are very distant, meaning we're seeing them as they were billions of years ago when the universe was young. They were much more common in the early universe when supermassive black holes had more available fuel. Today, most supermassive black holes are quiescent, having exhausted their local supply of gas. Fact 41. The universe's structure is shaped primarily by dark matter, not ordinary matter. Computer simulations of cosmic structure formation show that without dark matter, the universe would look completely different. The gravity from ordinary matter alone isn't strong enough to explain how galaxies and galaxy clusters formed as quickly as they did. Dark matter acts as gravitational scaffolding. It collapses into dense halos first, creating gravitational wells into which ordinary matter falls. Stars and galaxies form within these dark matter halos, like visible ornaments hanging on an invisible framework. The distribution of dark matter determines where galaxies form and how they cluster. Without dark matter, the cosmic web wouldn't exist in its current form. Galaxies might not have formed at all, or would have formed much later, creating a fundamentally different universe. We live in a cosmos shaped by invisible matter, where what we see is only the luminous minority of the total mass. Fact 42. Some galaxies show no evidence of dark matter, challenging our understanding. In 2018, astronomers discovered NGC 1052-DF2, a galaxy that appears to contain little or no dark matter. This is strange because dark matter is supposed to make up most of the mass in galaxies. The discovery sparked controversy and debate. Some researchers suggest the galaxy might have lost its dark matter through tidal interactions with a neighboring galaxy, stripped away by gravitational forces. Others propose the galaxy formed in an unusual way that prevented it from accumulating much dark matter to begin with. Still others question whether the distance measurements to the galaxy are correct, which would change the calculation of its mass. These dark matter deficient galaxies are rare, but their existence is important. They show that dark matter and ordinary matter can be separated, which supports the idea that dark matter is made of particles distinct from ordinary matter. If dark matter were just a modification of gravity rather than actual matter, you wouldn't expect to find galaxies with and without it. Exoplanets and the search for life. Fact 43. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995. Michel Mayor and Didier Queloz detected 51 Pegasi b using the radial velocity method, watching for the tiny wobble in the star's motion caused by an orbiting planet's gravitational tug. The discovery was revolutionary and surprising. The planet was a gas giant, about half the mass of Jupiter, but it orbited extremely close to its star, completing an orbit every 4 days. Such hot Jupiters were completely unexpected. In our solar system, gas giants orbit far from the Sun. The existence of 51 Pegasi b showed that planetary systems could be arranged very differently from our own. Mayer and Queloz received the Nobel Prize in Physics in 2019 for this discovery, which opened the floodgates. In the nearly 3 decades since, thousands of exoplanets have been discovered, revealing an incredible diversity of worlds. Planets are not rare, they're common, and most stars have at least one planet orbiting them. Fact 44. More than 6,000 exoplanets have been confirmed, with thousands more candidates awaiting verification. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized exoplanet discovery. It stared at a single patch of sky containing about 150,000 stars, looking for the tiny dimming that occurs when a planet passes in front of its star from our perspective. This transit method is incredibly sensitive, able to detect Earth-sized planets around sun-like stars. Kepler discovered more than 2,600 confirmed exoplanets and thousands of candidates. The TESS mission, launched in 2018, is continuing this work across the entire sky. Ground-based observatories contribute too, using radial velocity measurements, direct imaging, and gravitational microlensing. Each discovery teaches us something new about how planets form, what kinds of planets are possible, and how common different types of planetary systems might be. We now know that planets are not special to our solar system, but are a natural outcome of star formation throughout the galaxy. Fact 45. The habitable zone is the region around a star where liquid water could exist on a planet's surface. Liquid water is essential for life as we know it, so the habitable zone, sometimes called the Goldilocks zone, is a key concept in the search for potentially habitable worlds. The zone's location and size depend on the star's temperature and brightness. For cooler, dimmer red dwarf stars, the habitable zone is much closer to the star. For hotter, brighter stars, it's farther out. A planet in the habitable zone isn't guaranteed to be habitable. It needs an atmosphere to maintain liquid water, appropriate mass to retain that atmosphere, and various other factors need to align. Mars is technically in the Sun's habitable zone, but it has little atmosphere and no liquid water on its surface. Venus is near the inner edge and is hellishly hot due to a runaway greenhouse effect. Earth is in the sweet spot, but even here, life friendliness requires numerous factors beyond just distance from the Sun. Fact 46. Some exoplanets orbit in the habitable zones of their stars and are roughly Earth-sized. These worlds are prime candidates in the search for life beyond Earth. Proxima Centauri b, orbiting the closest star to our Sun, at just 4.2 light-years away, is a roughly Earth-mass planet in the habitable zone of its red dwarf star. Kepler, 452b orbits a Sun-like star at a distance similar to Earth's, though it's about 60% larger than Earth. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 of which orbit in the habitable zone. Some of these worlds might have oceans, atmospheres, and conditions suitable for life. But we don't know for sure. Detecting atmospheres on Earth-sized exoplanets is challenging because they're so small and far away. The James Webb Space Telescope is beginning to analyze the atmospheres of some larger exoplanets, looking for biosignatures, chemicals that might indicate the presence of life. For Earth-sized worlds, we'll need even more powerful future telescopes. Fact 47. Hot Jupiters are gas giant planets that orbit very close to their stars. These worlds are scorching hot, with surface temperatures often exceeding 1,000 degrees Celsius. They complete orbits in just a few days and are tidally locked, always showing the same face to their star, like the moon does to Earth. One hemisphere experiences eternal day, baked by stellar radiation, while the other experiences eternal night. Powerful winds transfer heat between the day and night sides, creating dynamic atmospheres with complex weather patterns. The existence of hot Jupiters puzzled astronomers. Gas giants should form far from their stars, where ice and volatiles can condense. The prevailing theory is that these planets formed farther out and then migrated inward, either through gravitational interactions with the gas disk from which they formed, or through interactions with other planets. Some may have had planetary companions that they ejected during their inward migration, reshaping their entire planetary systems. Fact 48. Some exoplanets are rogue worlds, drifting through space unbound to any star. These orphan planets were either ejected from their birth planetary systems through gravitational interactions, or formed in isolation from the collapse of small gas clouds. Estimates suggest there could be billions of rogue planets in the Milky Way, possibly outnumbering stars. Without a star to warm them, these worlds are cold and dark, with surface temperatures barely above absolute zero. But some might retain heat from their formation, or from radioactive decay in their cores. A sufficiently large rogue planet could have enough internal heat to maintain subsurface liquid water, potentially even harboring life in underground oceans, completely independent of any star. These lonely worlds wander the galaxy, invisible except when they pass in front of a background star and briefly magnify its light through gravitational microlensing. They represent a type of planet that doesn't exist in our solar system, nomads of the cosmic void. Fact 49. Super-Earths are a common type of exoplanet, but we don't have one in our solar system. Super-Earths are planets more massive than Earth, but lighter than ice giants like Neptune, typically with masses between 1 and 10 times Earth's mass. They're one of the most common types of exoplanets discovered, yet our solar system doesn't have one. This gap in our planetary population makes it harder to understand what super-Earths are like. Are they scaled-up rocky planets, or are they more like mini-Neptunes with thick hydrogen atmospheres? The answer probably depends on their mass and formation history. Some super-Earths orbit in habitable zones and could potentially support life if they're rocky and have appropriate atmospheres. Understanding these worlds is crucial because they're abundant in the galaxy. If we're searching for life beyond Earth, super-Earths might be where we find it. Fact 50. The James Webb Space Telescope has begun detecting atmospheres on some exoplanets. JWST's infrared capabilities allow it to analyze the atmospheres of exoplanets by observing starlight filtering through the atmosphere during a transit. Different molecules absorb light at different wavelengths, creating a spectral fingerprint. JWST has detected water vapor, carbon dioxide, sulfur dioxide, and other molecules in the atmospheres of several exoplanets. In 2023, it studied the atmosphere of exoplanet K 218b, a sub-Neptune in the habitable zone. Some researchers reported potential but tentative evidence of dimethyl sulfide, a molecule that on Earth is primarily produced by life. However, this detection remains uncertain and highly debated, requiring further observations and analysis to confirm. The search for biosignatures, chemicals that might indicate life, is one of JWST's most exciting missions. Finding atmospheric compositions that are far from chemical equilibrium, or detecting molecules like oxygen and methane together, could suggest biological activity. We might be on the verge of detecting signs of life on a world orbiting another star. Fact 51. Some exoplanets have been directly imaged. Most exoplanets are detected indirectly, through their effects on their stars, but a few have been photographed directly. This requires blocking out the star's light, which is millions of times brighter than the planet, and then detecting the faint light from the planet itself. Direct imaging works best for young, massive planets that are still hot from their formation and orbiting far from their stars. The first directly imaged exoplanet was 2M1207b, discovered in 2004. Since then, dozens of others have been photographed. These images are usually just a few pixels, but they're actual pictures of worlds orbiting other stars. Future telescopes will improve direct imaging capabilities, potentially allowing us to photograph Earth-like planets and analyze their light for signs of continents, oceans, clouds, and maybe even vegetation. Imagine seeing another Earth, a pale blue dot orbiting a distant star, knowing that it might harbor life. Fact 52. The star TRAPPIST-1 has 7 Earth-sized planets, the most of any known system. This ultra-cool red dwarf star, located 40 light-years away, is surrounded by a compact planetary system. All 7 planets orbit closer to their star than Mercury orbits the Sun. But because TRAPPIST-1 is so cool and dim, 3 of the planets are in the habitable zone. The planets are likely tidally locked, with permanent day and night sides. But atmospheric circulation might distribute heat. Several of the TRAPPIST-1 planets have densities, suggesting they could be rocky, and some might have water. The James Webb Space Telescope has begun studying their atmospheres, and early results suggest at least one planet, TRAPPIST-1d, likely has no atmosphere, though observations continue for the others. This system gives us 7 laboratories to study how planets form and evolve around cool stars, which are the most common type of star in the galaxy. If life exists in the TRAPPIST-1 system, it would be under a dim red sun, in a sky where the planet's siblings would appear larger than the Moon does from Earth. Fact 53. Planetary systems can have very different architectures from our solar system. In our solar system, small rocky planets orbit close to the Sun, and large gas giants orbit farther out. But many exoplanetary systems have gas giants very close to their stars, with smaller planets farther out, or planets in highly elliptical orbits, rather than the nearly circular orbits in our solar system. Some systems have planets in resonant orbits, where their orbital periods are related by simple ratios, locking them in gravitational dances. The diversity of planetary architectures suggests that planet formation and evolution can follow many paths depending on initial conditions and subsequent gravitational interactions. Our solar system isn't a template for how planetary systems must be arranged. It's just one possibility among many. This diversity makes predicting what kinds of planets might exist around any given star difficult, but it also means the galaxy might contain worlds stranger and more wonderful than we've yet imagined. Fact 54. We've discovered planets orbiting binary star systems. These circumbinary planets orbit both stars of a binary pair. If you stood on one of these worlds, you'd see two suns in the sky, like the fictional planet Tatooine from Star Wars. The Kepler mission discovered several such planets, including Kepler 16b, the first confirmed circumbinary planet around a main sequence star binary. These planets are interesting because their formation is complicated by the gravitational influence of two stars. The orbits must be stable despite the complex gravitational environment, and the habitable zone moves depending on whether one or both stars are warming the planet. Life on a circumbinary planet would experience more complex seasonal variations, with day length and climate depending on the positions of both stars. These systems show that planets can form and survive in gravitational environments we once thought too chaotic to allow planetary formation. Fact 55. The search for life beyond Earth includes looking for technosignatures from advanced civilizations. While biosignatures are chemicals that might indicate life, technosignatures would be signs of technology. This could include radio signals, laser pulses, megastructures like Dyson spheres that harvest a star's energy, or atmospheric pollution from industrial processes. The search for extraterrestrial intelligence, or SETI, has been scanning the skies for radio signals since the 1960s. More recently, projects like Breakthrough Listen have expanded the search across broader frequency ranges and more stars. So far, we haven't detected any confirmed signals from alien civilizations, but the search continues. The Fermi paradox asks, if intelligent life is common, where is everybody? Why haven't we seen obvious signs of alien civilizations? Maybe life is rare. Maybe technological civilizations destroy themselves. Maybe they're out there but not broadcasting, or we're looking in the wrong way. Or maybe we just haven't been looking long enough. The universe is vast, and we've barely begun to search. Our solar system's wonders. Fact 56. Jupiter is so massive that it has its own miniature solar system. The gas giant contains more than twice the mass of all the other planets combined. It has at least 95 known moons, 4 of which are large enough to be planets themselves if they orbited the Sun independently. The Galilean moons, Io, Europa, Ganymede, and Callisto, are fascinating worlds. Io is the most volcanically active body in the solar system, with hundreds of volcanoes erupting constantly due to tidal heating from Jupiter's gravity. Europa has a global ocean beneath its icy crust, making it one of the best places to search for life in our solar system. Ganymede is the largest moon in the solar system, bigger than Mercury, and has its own magnetic field. Callisto is heavily cratered, its surface preserving a record of impacts spanning billions of years. Jupiter's powerful gravity has shaped these moons, creating environments that might harbor life or that teach us about geological processes under exotic conditions. Fact 57. Saturn's rings are made of billions of chunks of ice and rock. These particles range in size from grains of sand to house-sized boulders, all orbiting Saturn in a thin disk. The rings are incredibly wide, extending more than 280,000 kilometers from the planet, but remarkably thin, in some places only tens of meters thick. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper. Despite their grand appearance, the rings contain surprisingly little total mass, less than some of Saturn's smaller moons. The rings might be relatively young, perhaps only a few 100 million years old, formed when a moon or comet was torn apart by Saturn's gravity, or shattered in a collision. They won't last forever. Ring particles are gradually spiraling into Saturn, raining down on the planet. In perhaps 100 million years, Saturn might have lost its rings entirely, becoming a naked gas giant. We're fortunate to live at a time when we can see Saturn adorned with its beautiful but temporary ornaments. Fact 58. Venus is the hottest planet in our solar system. Even though Mercury is closer to the Sun, Venus has a thick atmosphere of carbon dioxide, creating an extreme greenhouse effect that traps heat. Surface temperatures average about 465 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is about 92 times Earth's, equivalent to being a kilometer beneath the ocean on Earth. The atmosphere is filled with clouds of sulfuric acid. It's a hellish environment, completely inhospitable to life as we know it. But Venus wasn't always this way. Evidence suggests Venus might have once had oceans and a more temperate climate billions of years ago. A runaway greenhouse effect transformed it into the inferno we see today. Understanding what happened to Venus might teach us about climate change and habitability. Venus and Earth are similar in size and composition, yet their evolutions diverge dramatically. Studying Venus helps us understand the fine line between a habitable world and a hostile one. Fact 59. Mars has the largest volcano in the solar system. Olympus Mons rises about 22 kilometers above the Martian surface, nearly 3 times the height of Mount Everest. Its base is about 600 kilometers across, roughly the size of France. It's a shield volcano, similar to the volcanoes in Hawaii, but enormously larger. On Earth, plate tectonics move the crust, so volcanoes don't remain over hotspots long enough to grow this large. But Mars lacks active plate tectonics, so Olympus Mons could build up over billions of years as lava piled upon lava, creating a mountain so large its summit would be above most of the Martian atmosphere. The volcano is likely extinct now, but it's a monument to Mars's ancient geological activity, a reminder that the red planet was once a more dynamic world with flowing lava and possibly even rain. Fact 60. There's evidence suggesting subsurface liquid water might exist on Mars. While Mars's surface is too cold and its atmosphere too thin for liquid water to exist openly, radar observations from 2018 detected what could potentially be a lake of liquid water beneath Mars's south polar ice cap. If this interpretation is correct, this water would be kept liquid by the pressure of the ice above it, and possibly by dissolved salts that lower water's freezing point. However, alternative explanations for the radar signals have been proposed, and the presence of liquid water remains debated among scientists. Liquid water is essential for life as we know it, so if subsurface water does exist on Mars, it raises intriguing possibilities for microbial life in these hidden reservoirs. Mars also has recurring slope lineae, dark streaks, that appear on steep slopes during warm seasons. These features might be caused by flowing briny water, though other explanations involving dry flows have also been proposed. Understanding Mars's water, past and present, is crucial for understanding whether the planet ever supported life or could support future human explorers. Fact 61. Europa, Jupiter's moon, has an ocean beneath its icy shell that might contain more water than all of Earth's oceans combined. The moon is covered in a thick layer of ice, crisscrossed with cracks and ridges, suggesting the ice floats on a global liquid water ocean. Tidal forces from Jupiter's gravity flex Europa's interior, generating heat that keeps the ocean liquid despite the moon's distance from the sun. This ocean might be in direct contact with a rocky seafloor, creating hydrothermal vents like those on Earth's ocean floor. On Earth, Such vents support rich ecosystems of organisms that don't depend on sunlight. Could similar life exist in Europa's dark ocean? We don't know, but the possibility is tantalizing. Future missions are planned to orbit Europa and possibly even penetrate its ice to sample the ocean below. Finding life there would revolutionize our understanding of biology and show that life can emerge in environments very different from Earth's surface. Fact 62. Enceladus, a small moon of Saturn, has geysers that shoot water into space. The Cassini spacecraft discovered these plumes erupting from cracks near Enceladus' south pole. The geysers eject water vapor and ice particles at speeds fast enough to escape the moon's weak gravity, feeding Saturn's E-ring. These geysers provide evidence of a subsurface ocean, and Cassini flew through the plumes and analyzed them, detecting water, organic molecules, and salts. The presence of organics and energy from tidal heating makes Enceladus another prime candidate for life. The plumes offer a convenient way to sample the ocean without having to drill through kilometers of ice. We could send a spacecraft to fly through the plumes and analyze them more thoroughly, searching for biological molecules or even microorganisms. Enceladus is a tiny world, only about 500 kilometers in diameter, yet it might harbor life, showing that habitability doesn't require Earth-like conditions. Fact 63. Titan, Saturn's largest moon, has lakes and seas of liquid methane and ethane. It's the only body in the solar system, besides Earth, known to have stable liquid on its surface, though the liquid is hydrocarbons rather than water. Titan's thick nitrogen atmosphere creates weather patterns, with clouds and rain and seasonal changes. The surface temperature is about minus 179 degrees Celsius, far too cold for liquid water, but perfect for liquid methane. The Huygens probe, which landed on Titan in 2005, found rounded rocks, evidence of liquid flow. Radar images from Cassini revealed lakes concentrated near the poles. Titan's methane cycle is analogous to Earth's water cycle, with evaporation, cloud formation, rain, rivers, and lakes. This moon is a laboratory for studying organic chemistry in a cold environment, chemistry that might have been similar to the early Earth before life began. Titan might teach us about the chemical steps that lead to life. Fact 64. The asteroid belt between Mars and Jupiter contains millions of rocky bodies. Despite what science fiction might suggest, the asteroid belt isn't densely packed. The asteroids are spread out over such a vast volume that spacecraft can pass through without much risk of collision. The total mass of all asteroids combined is less than that of Earth's moon. These rocky remnants are leftovers from the solar system's formation, prevented from accreting into a planet by Jupiter's strong gravitational influence. Asteroids come in various compositions. Some are rocky, some metallic, some carbon-rich. They're time capsules, preserving material from the early solar system relatively unchanged. Studying asteroids helps us understand the conditions and processes that form the planets. Some asteroids have been visited by spacecraft, and we've even brought samples back to Earth for detailed analysis. Fact 65. The Kuiper Belt, beyond Neptune's orbit, contains thousands of icy bodies. Pluto is the most famous Kuiper Belt object, though it's no longer classified as a planet. The Kuiper Belt extends from about Neptune's orbit at 30 astronomical units out to about 50 AU from the Sun. It's similar to the asteroid belt, but much larger, and contains mostly icy objects rather than rocky ones. These frozen worlds are composed of ice, rock, and organic compounds. Many are remnants from the solar system's formation, pristine samples of the material that existed in the outer solar system 4.6 billion years ago. The New Horizons spacecraft flew by Pluto in 2015, revealing a complex and geologically active world with mountains of water ice and plains of frozen nitrogen. In 2019, New Horizons visited another Kuiper Belt object, Arakoth, a contact binary that looks like a snowman, providing insights into how planetesimals gently merged in the early solar system. Fact 66. The Sun's corona is much hotter than its surface. The Sun's visible surface, the photosphere, has a temperature of about 5,500 degrees Celsius. But the corona, the outermost part of the Sun's atmosphere visible during solar eclipses, reaches temperatures of over 1 million degrees. Why the corona is so much hotter than the surface is a long-standing puzzle called the coronal heating problem. Energy must be transported from the cooler surface to the hotter corona, but the mechanisms aren't fully understood. Magnetic fields probably play a role, storing energy that's suddenly released, heating the corona. The Parker Solar Probe, launched in 2018, is flying closer to the Sun than any previous spacecraft, directly sampling the corona to study its properties and try to solve this mystery. Understanding coronal heating might also help us predict space weather, which can affect satellites and power grids on Earth. Fact 67. Comets are icy bodies that develop glowing tails when they approach the Sun. These dirty snowballs spend most of their time in the distant outer solar system, cold and inactive. But when a comet's orbit brings it near the Sun, solar radiation heats the ice, causing it to sublimate into gas. This gas, along with dust freed from the ice, forms a glowing coma around the nucleus and a tail that can stretch millions of kilometers. The tail always points away from the Sun, pushed by the solar wind and radiation pressure. Comets are thought to originate from the Kuiper Belt, or the more distant Oort cloud, a spherical shell of icy bodies surrounding the solar system, extending halfway to the nearest star. Occasionally, gravitational perturbation send a comet falling toward the inner solar system, where it puts on a spectacular show before returning to the darkness, not to be seen again for decades, centuries, or millennia. Comets might have delivered water and organic molecules to early Earth, potentially seeding our planet with the ingredients for life. Cosmic phenomena and forces. Fact 68. Cosmic rays are high-energy particles that constantly bombard Earth from space. Most are protons, though some are heavier atomic nuclei or electrons. They originate from various sources: the Sun, supernova remnants, and even from outside our galaxy. When cosmic rays strike Earth's atmosphere, they collide with atoms, creating showers of secondary particles that rain down toward the surface. Some of these particles reach the ground and even penetrate deep underground. You're being struck by cosmic ray secondaries right now, about 1 particle per square centimeter per second passing through your body. Most pass harmlessly through, but over a lifetime, cosmic rays contribute a small amount to your total radiation dose. At high altitudes and in space, the flux is much higher, and astronauts must be protected from cosmic radiation. Understanding cosmic rays helps us study energetic processes in the universe and the space environment around Earth. Fact 69. The solar wind is a stream of charged particles flowing outward from the Sun. The Sun's corona is so hot that its particles have enough energy to escape the Sun's gravity, streaming out into space at speeds of 300 to 800 kilometers per second. This plasma of protons, electrons, and heavier ions fills the solar system, creating a bubble called the heliosphere. When the solar wind encounters Earth, it's deflected by our planet's magnetic field, flowing around us like water around a stone in a stream. But some particles get trapped in Earth's magnetic field, forming the Van Allen radiation belts. During solar storms, the solar wind intensifies, and particles can enter Earth's atmosphere near the poles, where the magnetic field lines converge. These particles collide with atmospheric gases, causing them to glow, creating the aurora, the northern and southern lights. The solar wind also shapes the tails of comets and can strip atmospheres from planets without strong magnetic fields. Fact 70. Earth's magnetic field protects us from harmful solar radiation generated by the motion of molten iron in Earth's outer core. Our magnetic field extends tens of thousands of kilometers into space, creating a protective cocoon called the magnetosphere. This field deflects most of the solar wind and cosmic rays, preventing them from reaching the surface. Without it, Earth's atmosphere would gradually be stripped away by the solar wind, as happened on Mars, which lost its global magnetic field billions of years ago. The magnetic field isn't static. It changes over time. The magnetic poles wander, and every few 100,000 years, the field reverses entirely, with north and south magnetic poles swapping places. We're overdue for a reversal based on the historical record, but predicting when it will happen is difficult. During a reversal, the field weakens, potentially exposing the surface to more radiation. Life on Earth has survived many reversals, but it could affect satellite operations and power grids. Fact 71. The interstellar medium is the matter that exists in the space between stars. It's not a perfect vacuum. Space contains gas and dust, though at incredibly low densities. In a typical region of the interstellar medium, there might be only one atom per cubic centimeter, far more diffuse than any vacuum we can create on Earth. Despite this low density, the sheer volume means there's a significant total mass of interstellar material. The interstellar medium is a mix of hydrogen and helium gas, heavier elements, and dust grains made of silicates and carbon. It's also threaded with magnetic fields and filled with cosmic rays. This medium is the raw material from which new stars form, and it's enriched by the ashes of dead stars, recycling material through generations of stellar birth and death. The interstellar medium isn't uniform. It has structure, with dense clouds, tenuous bubbles blown by supernova, and filaments shaped by magnetic fields, and turbulence. Fact 72. Supernovae can briefly outshine entire galaxies. When a massive star explodes, it releases as much energy in a few weeks as the sun will emit over its entire 10 billion year lifetime. The explosion expels the star's outer layers at speeds of tens of thousands of kilometers per second, creating an expanding shell of hot gas called a supernova remnant. The Crab Nebula is the remnant of a supernova that exploded in 1054 CE, observed and recorded by Chinese and Arab astronomers. The explosion was bright enough to be seen during the day for weeks. Supernovae are crucial for enriching the universe with heavy elements. Elements heavier than iron can only be created in the extreme conditions of a supernova or a neutron star collision. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all were forged in stellar explosions and scattered into space, eventually incorporating into new stars and planets. Fact 73. Gamma ray bursts are the most energetic explosions in the universe since the Big Bang. These bursts release more energy in a few seconds than the sun will emit in its entire lifetime. They come in two types: short gamma ray bursts lasting less than 2 seconds are thought to result from the merger of two neutron stars, or a neutron star and a black hole. Long gamma ray bursts lasting more than 2 seconds are associated with the collapse of very massive stars into black holes, a hypernova. Gamma ray bursts emit most of their energy in gamma rays, the highest energy form of light, along with beams of matter and energy moving at nearly the speed of light. Fortunately, gamma ray bursts are rare and almost always occur in distant galaxies. If one occurred within our galaxy and was pointed toward Earth, it could damage the atmosphere and cause mass extinctions. We've never observed a gamma ray burst from the Milky Way in recorded history, but it's possible one could happen in the future. Fact 74. Gravitational lensing allows us to see objects that would otherwise be too distant or faint. According to general relativity, mass curves, space-time, and light follows these curves. When a massive object like a galaxy cluster lies between us and a more distant galaxy, the cluster's gravity bends the light from the background galaxy, magnifying and distorting it. Sometimes this creates multiple images of the same background galaxy, or stretches it into arcs and rings. Gravitational lensing has allowed us to see some of the most distant galaxies in the universe, their light magnified by foreground clusters. It also helps us map the distribution of dark matter. Even though we can't see dark matter directly, we can see how it bends light, revealing where the dark matter is located. Some of the most dramatic images from the Hubble and James Webb Space Telescopes show gravitational lensing, with arcs of distant galaxies wrapped around massive clusters, space-time made visible. Fact 75. The speed of light in a vacuum is the universal speed limit. Nothing can travel faster than 299,792,458 meters per second. The speed of light, commonly denoted as c. This isn't just a speed limit for light, it's a fundamental speed limit built into the structure of spacetime. As objects with mass approach the speed of light, they require ever-increasing amounts of energy to accelerate further. Reaching the speed of light would require infinite energy, making it impossible for anything with mass. Light itself always travels at exactly c in a vacuum, never faster or slower. This speed limit has profound implications. It means information can't travel instantaneously across the universe. It takes time for light to travel between stars, between galaxies. When we look at distant objects, we're seeing them not as they are now, but as they were when the light left them, sometimes billions of years ago. The universe has a light speed horizon beyond which we cannot see. Fact 76. Time dilation means time passes at different rates depending on motion and gravity. According to special relativity, if you travel at a significant fraction of the speed of light, time passes more slowly for you compared to someone at rest. According to general relativity, time also passes more slowly in strong gravitational fields. These aren't illusions, they're real effects measured by precise clocks. GPS satellites experience time dilation because they're moving and because they're in a weaker gravitational field than clocks on Earth's surface. Without correcting for these relativistic effects, GPS would accumulate errors of kilometers per day. Time dilation means that astronauts on the International Space Station age slightly slower than people on the ground, though the effect is tiny, just a few milliseconds over months in orbit. In extreme cases near black holes, time dilation becomes dramatic, with time nearly stopping at the event horizon from an outside perspective. Fact 77. The universe is filled with neutrinos, ghostly particles that rarely interact with matter. Neutrinos are produced in nuclear reactions, including those in the sun's core, supernova explosions, and cosmic ray collisions. Trillions of neutrinos from the sun pass through your body every second. But because they interact so weakly with matter, they pass through without any effect. To detect neutrinos, we build enormous detectors deep underground or under ice, shielding them from other particles. Even then, We might detect only a handful of neutrinos out of the countless billions passing through the detector. Neutrino astronomy is a new field. Detecting neutrinos from the sun confirmed our understanding of solar fusion. Detecting neutrinos from supernova 1987A, which exploded in the Large Magellanic Cloud, gave us information about the supernova's core that we couldn't get from light. Neutrinos travel at nearly the speed of light and carry information from the densest, most energetic regions of the cosmos, places light can't escape from. Fact 78. Antimatter is real, and it's been created and studied in laboratories. For every particle, there's an antiparticle with the same mass but opposite charge. The antiparticle of an electron is a positron with positive instead of negative charge. When matter and antimatter meet, they annihilate, converting their mass entirely into energy, according to E equals mc squared. This annihilation is incredibly efficient, releasing far more energy per unit mass than any chemical or nuclear reaction. Antimatter exists naturally, produced in small amounts by radioactive decay, cosmic rays, and in particle accelerators. The challenge is storing it, because if antimatter touches ordinary matter, it annihilates. We can trap antimatter using magnetic fields, and researchers have successfully stored antihydrogen atoms for minutes. Why is the universe made of matter rather than antimatter? In the Big Bang, matter and antimatter should have been created in equal amounts and then annihilated, leaving only energy. Something must have caused a slight imbalance favoring matter, and understanding that asymmetry is one of the great unsolved problems in physics. The search for understanding. Fact 79. The Hubble Space Telescope has been observing the universe for more than 34 years. Launched in 1990, Hubble orbits Earth above the atmosphere, allowing it to capture incredibly sharp images across ultraviolet, visible, and near-infrared wavelengths. It has taken over 1.6 million observations, transforming our understanding of the cosmos. Hubble measured the expansion rate of the universe with unprecedented precision, confirmed the existence of supermassive black holes and galaxies, observed the atmospheres of exoplanets, imaged distant galaxies from when the universe was young, and provided stunning images of star-forming regions, planetary nebulae, and galaxies. The Hubble Deep Fields, images of tiny patches of sky revealing thousands of distant galaxies, showed us the universe's depth and beauty. Despite being designed for a 15-year mission, Hubble continues to operate, thanks to servicing missions by space shuttle astronauts. It has become an icon of space exploration, a window through which humanity has glimpsed the wonders of the cosmos. Fact 80. The James Webb Space Telescope observes the universe in infrared light. Launched in 2021, JWST is the largest and most powerful space telescope ever built. Its primary mirror is 6.5 meters in diameter, composed of 18 hexagonal, gold-coated segments. Observing in infrared allows JWST to see through dust clouds that block visible light, peer into star-forming regions, study the atmospheres of exoplanets, and most importantly, observe the most distant galaxies in the universe. Light from these galaxies has been redshifted by the expansion of the universe into infrared wavelengths. JWST has already discovered galaxies that existed just a few 100 million years after the Big Bang, earlier than expected. It's studying the composition of exoplanet atmospheres in unprecedented detail. It's observing the formation of stars and planetary systems. JWST is giving us a view of the universe we've never had before, answering old questions and raising new ones, pushing the boundaries of our knowledge. Fact 81. The Event Horizon Telescope created the first image of a black hole's shadow by linking radio telescopes across the entire Earth. This global network of telescopes acts as a single Earth-sized virtual telescope, achieving the resolution necessary to image the environment around a black hole millions of light years away. The first image, released in 2019, showed the supermassive black hole M87*, revealing a bright ring of emission surrounding a dark central shadow. A second image of our own galaxy's central black hole, Sagittarius A*, was released in 2022. These images are feats of engineering and coordination. Observations must be synchronized to within nanoseconds using atomic clocks. The data is so voluminous that it had to be physically shipped on hard drives because internet speeds weren't fast enough. The images match predictions from general relativity beautifully, confirming Einstein's theory in one of the most extreme environments in the universe. Fact 82. Gravitational wave astronomy is a new way to observe the universe. For most of history, we've studied the cosmos using light in various forms. But in 2015, the LIGO detectors made the first direct detection of gravitational waves, ripples in space-time caused by the merger of two black holes. This opened a completely new window on the universe. Gravitational waves carry information about events that emit little or no light, like black hole mergers. They allow us to study the physics of gravity in extreme conditions and to observe the universe in a way that's complementary to traditional astronomy. Since 2015, dozens of gravitational wave events have been detected, mostly from black hole mergers, but also from neutron star collisions. In 2017, a neutron star merger was observed both in gravitational waves and electromagnetic radiation, a multi-messenger observation that yielded insights into how heavy elements are formed and the behavior of matter at extreme densities. Fact 83. The Vera Rubin Observatory will survey the entire visible sky every few nights. Currently under construction in Chile, this ground-based telescope will have an 8.4-meter mirror and a huge field of view, allowing it to capture large swaths of sky in single images. Its mission is the Legacy Survey of Space and Time, which will create the largest astronomical movie ever made. Over 10 years, it will generate tens of petabytes of data, cataloging billions of stars and galaxies, tracking transient phenomena like supernovae and asteroid movements, and studying the nature of dark matter and dark energy through weak gravitational lensing. The survey will detect objects that change in brightness or position, alerting astronomers to supernovae, variable stars, near-Earth asteroids, and other time-sensitive events. It will create a dynamic map of the sky, revealing the universe in motion. The data will be publicly available, enabling discoveries by professional and amateur astronomers around the world. Fact 84. The Square Kilometre Array will be the world's largest radio telescope. This international project will build thousands of radio antennas spread across Australia and South Africa, with a total collecting area of about 1 square kilometre, hence the name. The SKA will be sensitive enough to detect extremely faint radio signals from the distant universe, including from the era before the first stars formed. It will map the distribution of hydrogen gas in the early universe, study the formation and evolution of galaxies, detect pulsars, and use them to study fundamental physics and search for radio signals that might indicate extraterrestrial intelligence. The SKA will generate enormous amounts of data, requiring supercomputers to process. It represents a major leap in our ability to observe the radio universe, complementing optical and infrared telescopes and providing a comprehensive view of cosmic phenomena across multiple wavelengths. Fact 85. Asteroid and comet impacts have shaped Earth's history. About 66 million years ago, an asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs, triggering massive wildfires, tsunamis, and ejecting so much debris into the atmosphere that sunlight was blocked for years. The resulting environmental catastrophe drove the non-avian dinosaurs and many other species to extinction. Life on Earth has been punctuated by such impacts. Smaller impacts occur more frequently, with significant ones every few centuries or millennia. NASA and other space agencies track near-Earth asteroids, and there are ongoing efforts to develop technologies to deflect potentially hazardous asteroids. In 2022, the DART mission successfully demonstrated that we can change an asteroid's orbit by impacting it with a spacecraft, a proof of concept for planetary defense. Fact 86. We've sent spacecraft beyond the solar system. Voyager 1, launched in 1977, is the farthest human-made object from Earth, now more than 24 billion kilometers away, well into interstellar space. Voyager 2 is also in interstellar space, taking a different path. These spacecraft are still sending back data about the environment beyond the sun's influence, where the solar wind gives way to the interstellar medium. They carry golden records, phonograph records with sounds and images representing life on Earth, a message to any extraterrestrial civilization that might find them billions of years from now. The voyages are expected to continue transmitting until about 2025, when their power supplies will be too weak. After that, they'll drift silently through space, monuments to human curiosity, carrying our greetings to the stars. Fact 87. The Kepler Space Telescope revolutionized our understanding of exoplanets before it ran out of fuel. Kepler discovered more than 2,600 confirmed exoplanets and thousands of candidates. It showed that planets are common, that many stars have multiple planets, and that small rocky planets are abundant. Kepler found planets in the habitable zones of their stars, planets orbiting binary stars, planets more massive than Jupiter, and planets smaller than Earth. Some of the planetary systems Kepler discovered are packed tightly, with multiple planets orbiting closer to their star than Mercury orbits the Sun. Kepler's mission ended in 2018 when it exhausted its fuel, but the data it collected will be studied for years. The TESS mission is continuing Kepler's legacy, searching for exoplanets around bright, nearby stars, worlds that can be studied in more detail by other telescopes. Fact 88. Space missions have visited all the major planets and many moons in our solar system. We've landed probes on Venus and Mars, orbited Mercury, Jupiter, Saturn, and even flown by distant Pluto. The New Horizons mission to Pluto revealed a world far more complex than expected, with nitrogen ice plains, water ice mountains, and an active geology that defies explanation for such a cold, distant world. The Juno mission is orbiting Jupiter, studying its atmosphere, magnetic field, and interior structure. The Cassini mission spent 13 years at Saturn, revolutionizing our understanding of the ringed planet and its moons. Each mission has revealed surprises, showing that our solar system is far more diverse and interesting than we imagined. Future missions aim to study Europa's ocean, Titan's lakes, and bring samples back from Mars. We're in a golden age of solar system exploration, with robots as our ambassadors to these distant worlds, the fabric of space and time. Fact 89. General relativity describes gravity not as a force, but as the curvature of space-time. Massive objects bend the fabric of space-time, and objects moving through this curved space-time follow paths called geodesics, which we perceive as the effect of gravity. Earth doesn't pull on the moon with a force, rather, Earth curves space-time around it, and the moon follows the natural path through this curved space-time, which happens to be in orbit. This framework has been confirmed by countless observations, from the precession of Mercury's orbit to gravitational lensing to the detection of gravitational waves. General relativity fundamentally changed how we understand the universe, showing that space and time are not fixed backdrops, but dynamic entities that interact with matter and energy. Near massive objects or at high velocities, these effects become significant, and Newtonian physics is insufficient. We need Einstein's vision of curved space-time. Fact 90. Quantum mechanics describes the behavior of matter and energy at the smallest scales. At atomic and subatomic levels, particles exhibit both wave-like and particle-like properties. The position and momentum of a particle can't both be known with arbitrary precision, a consequence of the Heisenberg uncertainty principle. Particles can exist in superpositions, being in multiple states at once until measured. Quantum entanglement allows particles to be correlated in ways that seem to defy classical logic, with measurements on one particle instantaneously affecting another, no matter the distance between them. Quantum mechanics is incredibly successful, underpinning modern technology from semiconductors to lasers to MRI machines. Yet it's deeply strange, with interpretations that challenge our notions of reality and causality. The double-slit experiment shows that unobserved particles behave like waves, passing through both slits and interfering, but observed particles behave like particles, passing through one slit or the other. Measurement itself seems to affect reality in quantum mechanics, a mystery that continues to provoke debate and philosophical inquiry. Fact 91. We haven't yet unified general relativity and quantum mechanics into a single theory. General relativity works beautifully at large scales, describing stars, galaxies, and the universe. Quantum mechanics works perfectly at small scales, describing atoms and particles. But in situations where both gravity and quantum effects are important, like at the singularity inside a black hole or during the first moments of the Big Bang, we don't have a complete theory. Attempts to unify these theories include string theory, loop quantum gravity, and other approaches, but none have been confirmed experimentally. Finding a theory of quantum gravity is one of the greatest challenges in physics. It would describe how space-time itself behaves at the Planck scale, the smallest meaningful length, about 1.6 times 10 to the power of minus 35 meters. At this scale, space-time might be quantized, foamy, or completely different from our everyday experience. Solving this puzzle would be a monumental achievement, potentially revolutionizing our understanding of reality. Fact 92. The vacuum of space isn't empty. According to quantum field theory, even empty space is filled with quantum fields, and these fields fluctuate, creating virtual particles that pop into and out of existence. These fluctuations have measurable effects. The Casimir effect, where two uncharged metal plates in a vacuum attract each other, is caused by quantum vacuum fluctuations being different inside and outside the gap between the plates. Vacuum energy associated with these fluctuations might be related to dark energy, the mysterious force accelerating the expansion of the universe. However, calculations of vacuum energy's magnitude are off by an enormous factor, one of the biggest discrepancies in physics. Understanding the quantum vacuum and its role in cosmology is an active area of research, blending quantum mechanics and general relativity in ways we're only beginning to explore. Fact 93. There are 4 fundamental forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is the weakest, but acts over infinite range and affects all matter. Electromagnetism, also infinite in range, governs the interactions of charged particles and is responsible for chemistry, light, and most everyday forces. The strong nuclear force binds quarks into protons and neutrons, and binds protons and neutrons into atomic nuclei. It's incredibly strong, but only acts over very short ranges. The weak nuclear force is responsible for radioactive decay and plays a role in nuclear fusion in stars. The electromagnetic, weak, and strong forces have been unified in the Standard Model of particle physics, a theory that describes how particles and forces interact. Gravity remains separate, described by general relativity. Physicists dream of a grand, unified theory that would encompass all 4 forces in a single framework, explaining the fundamental workings of the universe, from the smallest particles to the largest cosmic structures. Fact 94. The Higgs boson gives other particles mass. Discovered in 2012 at the Large Hadron Collider, the Higgs boson is a quantum of the Higgs field, a field that permeates all of space. Particles acquire mass by interacting with the Higgs field. The more strongly a particle interacts, the more massive it is. Particles that don't interact with the Higgs field, like photons, have no mass. The discovery of the Higgs boson was the last piece of the Standard Model to be confirmed experimentally. It explains why the W and Z bosons, which carry the weak force, are massive, while the photon, which carries the electromagnetic force, is massless. Understanding the Higgs mechanism is crucial for understanding the origin of mass and the structure of the universe. Yet mysteries remain, like why the Higgs boson has the mass it does, and whether there are other Higgs-like particles. Fact 95. Extra dimensions might exist beyond the 3 spatial dimensions we experience. Some theories, like string theory, propose that the universe has more than the 4 dimensions, 3 spatial, 1 temporal, we're familiar with. These extra dimensions would be compactified, curled up so small that we can't detect them directly. The specific way they're curled affects the properties of particles and forces in our 4-dimensional world. While there's no direct evidence for extra dimensions, they provide a possible framework for unifying gravity with the other forces. Experiments at particle accelerators search for signatures of extra dimensions, like missing energy carried off by particles moving into these hidden dimensions. If extra dimensions exist, understanding their geometry and properties could unlock profound insights into the fundamental structure of reality, explaining why the forces have the strengths they do and why certain particles exist. Fact 96. The anthropic principle suggests the universe's properties are compatible with the existence of observers. If the fundamental constants of nature, like the strength of gravity or the mass of the electron, were even slightly different, the universe might be radically different, perhaps unable to form stars, atoms, or life. This observation can be interpreted in different ways. Perhaps we live in one of many universes, a multiverse, and naturally we find ourselves in one that allows our existence. Perhaps the constants aren't arbitrary, but are determined by some deeper, unknown principle. Or perhaps it's simply a statistical fluke that the constants are what they are. The anthropic principle is controversial because it borders on philosophy rather than testable science, but it raises important questions about why the universe has the properties it does, and whether those properties are inevitable or contingent. Fact 97. Dark energy might be the energy of empty space itself, or it might be something more exotic. The simplest explanation for dark energy is a cosmological constant, a constant energy density filling all of space uniformly. Einstein introduced the cosmological constant in his equations of general relativity, then later called it his greatest blunder when the expansion of the universe was discovered. Ironically, observations now suggest the cosmological constant, or something very like it, is real. But the magnitude is a problem. Quantum field theory predicts a vacuum energy density that's 120 orders of magnitude larger than what we observe. This discrepancy is called the cosmological constant problem, one of the deepest puzzles in physics. Alternative explanations for dark energy include quintessence, a dynamic field that changes over time, or modifications to general relativity itself on cosmic scales. Understanding dark energy is crucial for predicting the universe's ultimate fate, the future and the unknown. Fact 98. The ultimate fate of the universe depends on the nature of dark energy. If dark energy remains constant, the universe will continue expanding forever, with galaxies beyond our local group eventually receding faster than light, disappearing beyond our cosmic horizon. The universe will become increasingly cold, dark, and empty, a scenario called the heat death or big freeze. Stars will exhaust their fuel, galaxies will fade, and eventually even black holes will evaporate through Hawking radiation over timescales of 10 to the power of 100 years or more. If dark energy increases over time, the expansion could accelerate without limit, tearing apart galaxies, stars, planets, and eventually atoms in a big rip. If dark energy decreases or reverses, the expansion could slow and eventually reverse, leading to a big crunch where the universe collapses back to a singularity. Current observations suggest the universe is heading for eternal expansion, but uncertainties remain. The far future is written in the properties of dark energy, a force we barely understand. Fact 99. We don't know if the universe had a beginning or if something existed before the Big Bang. The Big Bang theory describes the universe's evolution from an extremely hot, dense state 13.8 billion years ago, but it doesn't necessarily describe an absolute beginning. Some speculative theories propose the universe might be cyclical, expanding and contracting in endless cycles. Others suggest the Big Bang could have been a transition from a previous state, perhaps emerging from a quantum fluctuation. The concept of before the Big Bang might not even make sense if time itself began at the Big Bang. Inflation theory suggests the universe underwent rapid expansion in its first fraction of a second, but what might have caused inflation and what, if anything, preceded it remain open questions. We're probing the universe's earliest moments with observations of the cosmic microwave background and the large-scale structure of matter, but the absolute origin remains mysterious, perhaps fundamentally unknowable with current physics. Fact 100. The universe is far stranger than we imagine, and many mysteries remain unsolved. We don't know what most of the universe is made of. Dark matter and dark energy compose 95% of the cosmos, yet we don't know their nature. We haven't found a quantum theory of gravity. We don't know if there's life elsewhere in the universe, or if we're alone. We don't understand why the universe has the specific properties it does, why the fundamental constants have their values, or whether there are other universes beyond our own. The more we learn, the more questions emerge. Every answered question opens doors to new mysteries. This is the beauty of science and the wonder of exploring the cosmos. We stand at the edge of the unknown, equipped with curiosity and ingenuity, reaching out to understand the universe that made us. the journey is far from over. In fact, it may have only just begun.
Conclusion.
And now, as we return from our journey through these 100 facts about space, let the vastness settle gently around you. We've traveled from the first moments after the Big Bang to the farthest reaches of the observable universe. We've seen stars being born and dying, galaxies colliding, black holes devouring matter, and planets orbiting distant suns. We've glimpsed mysteries that remain unsolved and wondered at the elegant laws that govern all of existence. You are a part of this cosmos. The atoms in your body were forged in the hearts of stars, scattered by supernova explosions, and gathered into the planet we call home. You are made of the same substance as the stars, connected to the universe in the most fundamental way. The light from distant galaxies has traveled billions of years to reach your eyes. When you look up at the night sky, you're seeing not just across space, but across time, witnessing the universe as it was in the distant past. Tonight, as you rest, the universe continues its slow, majestic dance. Stars are forming, planets are orbiting, galaxies are spinning. Light is traveling through the endless dark, carrying information across the cosmic ocean. And you, a conscious observer made of stardust, are part of it all. A small warmth in the cold vastness, a brief moment of awareness in an ancient, ongoing story. If you found peace in these cosmic contemplations, if they've helped you drift into rest with a sense of wonder, please consider liking this video and subscribing to Whispered Knowledge. It helps others find their way here, one sleeper at a time. I hope you dream of stars and galaxies, of mysteries waiting to be discovered, and wake feeling connected to the beautiful, bewildering universe we call home. Sleep well, and may the cosmos cradle you gently. Good night.